Yeah, ladies and gentlemen, thank you very much for the introduction, and thank you very much, Daniel von Wachter, for inviting me to this talk. I enjoy this conference very much. I think it's a very exciting combination of speakers. So I'll be talking about causal closures, causal closure laws of nature and divine action, and I will have the following outline. First, I want to talk a little bit about the claim of causal closure and its influence, and the main part will then be on causal closure and the laws of nature, and finally on divine action, which will then be fairly briefly, and of course I will draw some conclusions. Now, let's start with the claim of causal closure, and you may be aware of Laplace demons. There are some demons in physics. One is Laplace and one is Maxwell, and the Laplacian one is a figure that is thought of knowing all future events or states of a system, preferably of the whole universe, and when they are uniquely determined by natural laws, then one can predict whatever is happening. So the knowledge of the governing natural laws and the initial conditions of a physical system allows, at least of course in principle, a unique calculation of the development of its future states. So this is causal closure, is determinism, plus the assumption that no forces whatsoever act upon the world. So the world is a closed system in itself. And if we know all these governing laws and initial conditions, then we can predict what is going to happen. So if this is true, then from the Big Bang it was clear that there will be this meeting, that we will be sitting here, that I will give this talk, that Mr. Tapp is giving the reply, and what I answer will also be clear, and what you ask will be clear, and what I answer will be clear. So everything is determined and is clear right from the beginning. Now, this has had profound impact on Protestant theology, also on some Catholic, but maybe on Protestant theology. And the main, the most clear description is given, as far as I know, by Ralf Bergmann in Neues Testament und Mythologie, New Testament and Mythology. And there he claims that science and technology have developed so far that no man can seriously stick to the worldview of the New Testament. And then he writes, relevant for the theology is only the question how the decision for a consequently biological worldview, which he means a naturalistic worldview, can be justified. And this is first given by the worldview formed by the natural science, and then by the self-conception of man, who understands himself as closed inner unit which is not open for the access of supernatural powers. So there is a closure of man to supernatural powers, and that's based on the worldview determined by the 19th century concept of natural science. Now, this is not just theory, but this has profound impact found in the program of demythologization, complicated word in English, and Mythologisierung in German. And for me, the excerpt of what Bergmann was saying was, reports of miracles of the New Testament are myths expressing underlying truths, but no historic encounters. The second statement is humans are closed units with respect to supernatural powers, and this especially means that God cannot act on humans. Surprisingly, the third statement he makes is that God acts in the life of Jesus. So I was always wondering why theologians didn't bring up this point. I'm not going into historic critical method and this kind of stuff, that's stuff for the theologians, but in my view, the program of demythologization is self-contradictory, and nevertheless has had a huge impact on Western Christianity and on thinking in Christian theology. So, does this work? Is this correct? I want to tackle this question with this main chapter of the talk, causal networks and the laws of nature. First, I would like to start with the clockmaker's universe I've introduced before. Then I will talk about natural laws and equation of motions. Then on conservation of energy, invariance, and symmetry, to understand how conservation laws come about. Okay. Then I will talk about deterministic chaos. I don't know if that's an outflow of that. Quantum mechanics and statistical physics. So, to repeat, deterministic chaos, quantum mechanics, and statistical physics. And then draw some conclusion on divine action. So let's start with the first part, the clockmaker's universe. I rely on a fairly intuitive concept of causation. There is a cause and an effect. There is an earthquake in the sea, and that causes a tsunami, and the tsunami damages the nuclear power station, and then the story goes on. So basically what we have is we have a chain of causes and effects. And the first thing I would just like to mention without elaborating much on it is that physics cannot describe a first cause. So physics works with some initial condition and then calculates what's going on. If there is nothing, then we cannot do any calculation, so we cannot give any account on a first cause. Now, what happens in the real world? We have a dense network of causes and effects, and we cannot even always uniquely determine a set of causes that brought about these effects here. There may be various kind of connections which leads to the same effect. If you wake up in the morning with a headache, you may have drunken too much, but there may also have been other reasons why you wake up with a headache. So that's not easy to say what happened. What we can do in this case very successfully is to treat a direct problem, typically treated by partial differential equations. When we have the initial and boundary conditions, we calculate what is happening here. So let us come to the question, what are natural laws doing in this scheme, and what are equations of motions? Here I have a natural law, which I think definitely is a natural law. We had a discussion on that yesterday, saying from classical mechanics, Newton's law, that force equals mass multiplied by acceleration. Now, what I need to know is what is the force that acts here, and when I have the force, then I can calculate the equation of motion. So we have to define a special case, and the question here is, how does a mass behave when it's dropped from a height h? I took this because it is the most simplest case I could ever think of, so I take this one. The gravity, the force of gravity and the calculation of the Earth revolving the Sun is much more complicated, so this is really the most simple case I can think of. You take a stone and drop it, and you want to know what is happening here. So the force acting on the mass is given by the Earth's gravitational acceleration, and that is just minus m multiplied by g, minus because the stone is dropping down. So F is minus m multiplied by g, and that's m multiplied by a. So our equation simply is acceleration equals minus g. So at this point, I have a little problem in my talk. If I follow the rule that you lose half of the audience with every equation, then the audience will soon be gone. So if you don't like equations, just relax a little bit and just listen to the conclusions. If you like equations, you have more benefit from it because you understand why it's coming about. So basically, the simple equation describes what is happening here, but in order to calculate the equations of motions, we have to do a little bit more. I will skip out the calculations. There's two simple integrals. I don't want to bore you with that one. We have here one initial condition if the initial velocity is 0. So if you just drop the stone, then you get an equation of motion that looks like this one here. So we have the height minus half g multiplied by the square of the time. If you decide to throw the stone up then of course it moves a little bit in this direction and then falls down. So the initial condition is that the velocity is not 0, then the equation of motion changes. So we have an additional part here that describes the effect of the initial velocity here. So the simple message that I want to derive here is that the law of nature does not change. It's always the same, but the equations of motion change, and they change due to the initial conditions. And if I would have chosen 2 or 3-dimensional problems, there would also be boundary conditions which I have to define. If I define them, then I have the trajectory. And I can always impede the process. I can always throw the stone at another direction or catch it or whatever. Always the effect will be that the equations of motions change, but the natural law will not change. So whatever you do, whatever action you do, there is no change in the natural law. And this is, I think, some misconception that people have. If you somehow interact, or if God interacts with the world, then natural laws are broken. This is just not the case. If anyone interacts with the world, then the equations of motion change, but not the natural laws. So, the next objection to divine action is conservation of energy. Conservation of energy has is an effect of invariance and symmetries. And now comes the worst part. The idea is to formulate so-called Hamilton-Lagrange formalism that delivers an alternative description of classical mechanics. It's much more complicated, but it's more powerful. It enables the discovery of more general principles, and it forms the basis for the formalism, for example, of quantum mechanics. Now, if we go through this, then we have to observe the Hamilton principle for conservative systems. So there are not only conservative systems in politics, but also in physics. And a conservative system means basically there's no friction, to be simple here. And what we do here is we describe a configuration space, for example, with the coordinates q1 and q2. This could be x and y, but this could be also other coordinates. And we have a mass or any object at point t1, and we want to know how does it move to the point t2. What trajectory does it take? And in principle, it could take any trajectory, whatever you think. It could go this way around and somehow go here or wherever, but it doesn't do it. And the question is, why does it take the trajectory that we expect? And the actual trajectory that is taken corresponds to a minimum of action. Now, action is energy multiplied by time, and if that is minimized, we find the equation of motion. And that is done by looking at the integration of this path from point t1 to point t2 over a function L, that's the Lagrange function, over time. And this Lagrange function is defined as a difference between kinetic and potential energy. And if we go through the formalism and do everything correct, then we find that L depends on the time, depends on the generalized coordinates, q1, 2, 3, n, whatever, and their generalized derivatives, which is the time derivation from these coordinates. So every mechanical system can be described by a Lagrange function which depends on the generalized coordinates, the generalized velocities, and the time. Now, what can we learn from this? We find the equation of motion by calculating this expression. So we have the partial derivative of the Lagrange function with respect to the generalized coordinates, and we have the partial derivative with respect to the velocities and the time derivation. One can show fairly easily that this is equivalent to Newton's law. I will not do that in order to not give you much more pain with formulas. But the important thing here is that every coordinate corresponds to a generalized momentum by this relation here. And now we can have a look what this Lagrange function looks like. And if we find that the Lagrange function does not contain the coordinate, then this coordinate can be ignored. You can see that from this formula here. If the Lagrange function does not is not dependent on Qi, then the derivation with respect to Qi is 0 and only this term is left. So we have this expression here, and this expression is the time derivation of the generalized momentum, and if that is 0, then the generalized momentum is constant. And this is the general result that we derive is the generalized momentum belonging to the corresponding coordinate is conserved. So a conservation law has a connection to a variable that does not have an influence on the system. And if we go through this formalism, then we find this invariance against a change of a coordinate, then the corresponding momentum is conserved, and the system has a symmetry with respect to this coordinate. Now, if we spell that out, then we find, for example, that if the Lagrange function is invariant against time, which means I can do an experiment now and I can do it tomorrow or yesterday or in a week or whatever, then we talk about a homogeneity of time. The time is sort of always the same. And we conserve the energy. If we have an invariance against a translation in space, which means I can do the experiment here, I can do the experiment here or on the South Pole or wherever, then we talk about homogeneity of space and we have the conservation of the linear momentum. When we have an invariance of the space against rotation, so we take our apparatus and rotate it and always find the same behavior, we talk about the isotropy of space and we have a conserved quantity of the angular momentum. These are the most simplest relations. You can get much more complicated relations with more abstract mathematical concepts, but I think this should do. And so that means a loss of symmetry corresponds to the failure of a conservation law. So conservation laws do not just come as some obscure principle, but they come as a consequence of symmetry and invariances. So now if we have a conservation law, then this conservation law is related to a continuity equation. So if a quantity is conserved, if energy is conserved, then a continuity equation must hold, which means the change of the amount of the quantity with time, in this case the change of energy with time, within a closed system is given by this equation, which means the change in the energy in the system is the difference of the inflow of energy minus the outflow of energy. So you can think of, for example, a battery which you charge. So when you let a current flow in, then you charge the battery until it's full, and when you extract current out of it, then you take energy out of it, so the energy would decrease. And if nothing else happens, like other effects which we don't want to consider here, then you should find out that the energy is conserved, so what flows out must decrease the energy content of the system here. So now we are so far that we can talk about the principle of energy conservation. And there are several definitions. And one is energy cannot be created or destroyed. Now this is a metaphysical principle. It cannot really be tested. What we can test is the total energy in a closed system is constant. That's something Robert Lama wrote a nice article about a couple of years ago. Or I would say more practically, the continuity equation for energy holds for a given volume. It's really difficult in practice to make a closed system. This involves quite a lot of effort. What you have to do in principle is you have to think about what are the inflowing and outflowing energies. So this is very complicated to do in practice if you want to do it very precisely. But in general, 2 and 3 can empirically testable. And then you can find out whether your system is has the quality of energy conservation. Now, in order to do this, of course, we have to have a complete knowledge of all kinds of energies and interaction mechanisms in the system, which we consider. And this is a prerequisite for a correct physical description. if we don't know one of the energy terms or whatever interacts, then we cannot make a valid description of the system. This is fairly important. Now, to make some conclusions out of this, under the influence of divine intervention, if there is one, then nature is obviously not a closed system, because if something interacts from outside, then we do not have a closed system. So we have to be very careful what we consider as a closed system. Now, if divine intervention takes place, it may or may not add energy to a given part of space-time. It's very hard to decide that, and it may depend on the special case. So we have to think about, can we expect energy changes within such an interaction or not, or may it be so minute that we cannot detect it? And the third point is, we do not know the details about the mechanism God uses to act in the world if he then acts. So I think this is a big obstacle for naturalists, that if you are a naturalistic person, then you know the whole system, or you think you know the whole system. This is nice because you can describe just everything. But if you're not a naturalist, then you deal with part of the system which you cannot really describe, and that is cumbersome. That is something you do not really want. But if we take into account that there is a God and that he may act, if there are good reasons for that, then we are in the situation that part of the system, so to say, is not well known. And that's just something we have to deal with. So, but that's not the worst part of the story. The worst part comes now. Deterministic chaos, quantum mechanics, and statistical physics. We are very much used to use examples from classical mechanics. We have a mass that falls to the ground. We have two masses that rotate around each other, and all these simple kind of situations, but that's not the real world. Now, what is deterministic chaos? Chaos normally comes about. Can you switch the light off? Normally comes about by the situation that small deviations of initial conditions lead to strong and sometimes unpredictable differences in outcome. So if you have a linear system, for example, if I throw the pointer, I throw it a bit higher, then it would end up further in the back. If I throw it a bit lower, then it would end up in the first row. And I know by adjusting the angle that I'm throwing this, where it ends up. If that was a chaotic system, I could throw the pointer and it could end up here or wherever. So that's a characteristic of a chaotic system. Now, with deterministic, what we call deterministic chaos is a system where a small deviation of the initial conditions in a nonlinear system governed by deterministic equations in a limited volume typically leads to chaos. I wrote typically because there are some bizarre cases where you can have other combinations, but the typical characteristics would be nonlinearity, deterministic equations, and a limited volume, for example, in the stock market. So, typically, these conditions lead to chaos. Now, one of the most simplest examples that we can find in mechanics is a double pendulum. So, it's not a single pendule with some connection with a mass on it, but it has two masses which can move independently, and if you let this swing and go to certain amplitudes, then suddenly this motion becomes erratic, and there are nice movies in the internet, you can see that, where this flips around in such an unpredictable way. So in this case there is no quantum mechanics, it's just the nonlinear equations, it's just these properties that we have that create this nice erratic movement of the pendulum. Now, of course, not every one of you will have this nice double pendulum in your home. Sometimes one gets the impression that a deterministic chaos is not really something that is valid or that is relevant. But there's another example. You may have seen this chart here. Before I came, I went to the TV information in the internet from the 8th of September here on Friday, and they have this nice prediction, this nice 14-day weather forecast here. And what you see is that I took this on Friday, so on Friday they know what the temperature is, obviously, because they can measure it. And then they predict a temperature that goes like this. And here's the error bar. So what you see is the error is sort of exponentially, I don't know if it's really exponentially, but the error is increasing with time. So if you want to know what is happening on Sunday or on Wednesday because you want to have your garden party, then you may end up between 14 degrees, which is not very nice, and 22 degrees, which is okay. But no one can tell you, or no one could have told you on Friday. And that is not because they don't have nice computers. They buy racks and racks of computers and let them work in parallel. But there's a principal reason for it, because it's a system that works with deterministic chaos. So this is something that you experience in your daily life. But there is more to it. It's also relevant for a technical system. This is an example from fluid dynamics. You can have lots and lots of these examples where you see a tubular flow in a pipe, and you see here are the turbulences, and they come from the Navier-Stokes equations, which are nonlinear in a limited system. And when you drive the system into a higher Reynolds number, then you find these kind of situations here. And so chaos plays a big role in everyday life. In the technical world, you have to tame this turbulence in a way that it doesn't destroy your system. So the impression that you get when you drive your car, hopefully, or use other technical machines, that everything is running smooth and they are very deterministic, comes from the fact that you have hundreds and thousands of engineers working for years to make this system stable against any disruption. So the technical world that we normally use is sort of a little bit an artificial world, in the sense that a lot of people have worked on the fact that these things do not occur, but that these devices that you have work reliably. But nevertheless, all that is happening in nature, and is sometimes a lot of effort to get this under control. Now, there is another mechanism, we have talked about that yesterday, of chaos or of unpredictability, which comes from quantum mechanics. Here I've written down the Schrödinger equation. It's a deterministic equation. We have a wave function, and the time derivative of the wave function is influenced by the Hamiltonian, the Hamilton operator. And the Hamilton operator says something about the spatial derivatives and the potential where the particle moves in. And we have a deterministic equation, so everything should be fine, but the point here is that the probability to find a particle at a given point in space and time is given by the square of the absolute value. So I don't want to enter into a discussion like yesterday. The discussion about this nice little expression here is about 100 years old, and there are still competing explanations about that, but whatever we do, it seems we cannot get around the Heisenberg uncertainty principle, and we have this, this indeterministic behavior. And you can see that I would say this has an ontological character, but I'm only a simple physicist. I'm not a philosopher, so I say this with great care. Typically you can see this kind of experiments. Here you see electrons, where electrons hit a screen, and you have individual electrons going through a double slit, and if you have very few of them, you get this erratic sort of look here. If you have more and more electrons, and more turns into a picture that you can interpret as a maximum and a maximum and a minimum, and so you can calculate this pattern here, and we can very precisely calculate this pattern for many electrons, but we don't know what the individual electron is doing. So, coming back to our causal net of the world, we have this dense net of cause and effectors, and now we have an addition, which is a deterministic chaos and quantum mechanics, which adds probabilistic elements to this net, and this makes it very complicated. The direct problem works for a while and then breaks down, as we can see with the weather, and the inverse problem gets even worse. Now, let me make two remarks at this point. Knowing the results of dices, if you play this nice game, allows to reconstruct the state and go to this, the game and go to this state, if nobody cheats, of course, and everybody obeys to the rule. But the other way around doesn't work. Knowing the final state does not allow for reconstruction of the game, because there are a lot of ways to come from starting to the end point. Remark 2 is, some people think if you have a probability in the world, then the world must be chaotic. It must be somehow totally unpredictable, but that is not the case. There can be a balance between probabilistic and deterministic behavior. For example, what is the end result of this game? If you are patient enough to play with your children until the final end, then there is exactly one state that comes out after a finite, not after an infinite, but after a finite time. And this end state is this one here. There is no other end state of this game. So there can be situations where you have deterministic laws and probabilistic behavior that leads you, in spite of the probabilistic behavior, exactly to a certain end state. Now, I'm heading sort of to the climax here. Now you could say, okay, yeah, well, Newton's law is some law. Okay, there are many laws of nature, and we have in classical mechanics, we have this nice equation here, but it only holds for not too small and not too heavy objects, so medium masses like men, like cars, like trees, like whatever you have in everyday life, so that's fine. And you have to be well below the speed of light. If you do not obey to one of these conditions, then this equation doesn't work. So it's important to see that every equation has an area where it's valid, and there are other areas where it's not valid. And then if we have high masses, high velocities, we have to go to general relativity. So this equation looks a bit more complicated. We have a geometrical tensor, G mu, a gravitational constant, and an energy momentum tensor, T mu, and they are interlinked in this way. And generations of PhD students and other scientists have found special solutions to these problems. So there is a lot of knowledge about what kind of solutions come out of here. And but here still we have a problem, because it doesn't hold for small objects. It does not include quantum mechanics. So again, we have a very powerful law, and Newton's law is if you take this equation, take not too high speed and not too heavy masses, then you end up with classical mechanics again. So this is included in this one. Now, what we would like to have is, of course, quantum gravity, or the best would be a theory of everything. So I don't know which one it is, otherwise I would go to Stockholm. So I have to confine myself with these question marks here. And now the question came to my mind, if we have this theory of everything, can we then explain everything? So that's a big hope. We have this equation and we can do everything. That's of course not correct. And here I have gathered some ingredients for the death of a complete description of nature. And that is one is statistical mechanics that describes the behavior of ensembles. A large number of particles, and the information on the individual particles is lost, and it's in most cases also not important. What we do is we have an ensemble of particles, and we have an entropy, and the entropy is basically proportional to the logarithm of the number of states that a system can occupy. And what a system does is the ensemble tends towards a state with the maximum entropy, and that is the most likely state. So if anybody asks you about what is entropy, you can give an answer to that. It's the tendency to go towards the most likely state of the system. What else should it do? Now, there's a small problem with that, because you could argue, well, but if we have the supercomputer that can deal with 10 to the 23 particles and so on, then we could calculate very exactly what is happening, but that's not the case, because individual particles cannot be assigned a point-like state. So you cannot pinpoint a particle that's due to quantum mechanics to a point, but you have to leave the uncertainty in space and momentum. And so due to this, fluctuations are unavoidable. So you cannot have an ensemble of a lot of particles without fluctuations. And so this is an input also for some of the chaotic systems, for example, in fluid or gas dynamics. So, and the last point, or one of the last points, there's another one, is the system behavior depends on the surroundings, and that means, technically speaking, on initial and boundary conditions. So an equation does not, as I pointed out before, does not say what happens. You can only calculate what happens if you have these initial and boundary conditions. So to say, you always have to know something about the surroundings of the system. There is no isolated system in nature. It's always connected with some sort of outer world, and you can sometimes squeeze this outer world into the initial and boundary condition. But it comes even worse. Complex systems often or many times exhibit collective effects. For example, a gas has a temperature or a pressure. A solid body with many electrons has a Venn diagram and certain properties which the simple electron doesn't have. And so we have emergent phenomena. So the story of having natural law and then describing everything what happens just doesn't work. I don't want to talk about emergence. There's a talk later on which will talk about emergence as far as I've read, so I don't have to cover that, and it's too much anyway for one talk. So with this preliminary remarks, you should get a feeling about what a physical system, how a physical system is determined and how it is not determined, whether it's indeterminacy. So with that, we come to divine action, and that's a shorter part. I come back to this picture here. We have the dense net of causes and effects. We have the quantum mechanics or the deterministic chaos. So it looks something like the situation here. Of course, much more complicated, but in principle, that should do. Now, what happens if we have divine action? Divine action in a causal net would just add other causes and create other effects that have not been there before. So this would be the natural sort of flow of events, and now there comes a divine action, and we see other things happen which would have not happened otherwise. So this is fairly theoretical, and I want to give you two examples. I take an example of a miracle report in the New Testament. That's Matthew, New Testament, chapter 28, verse 2. And I don't want to talk about historic critical exegesis and things like that. I just assume that this report is somehow gives us some information on what is happening, so I don't want to go into the theological debate, but I just take this as an example. There was a great earthquake. The angel of the Lord came down from heaven and removed the stone and sat on it. And the context of this verse is the resurrection of Jesus, where the women come to the grave and there's a big stone in front of the grave, and they ask themselves, how can we get rid of the stone to go into the grave and prepare Jesus for his burial? Now they see the stone is removed and the cloth is lying here, and then there comes this explanation here. We don't know exactly how it comes about, but if you just for a moment take this as a description of divine action, then I would say nature just reacts according to the laws of nature upon human or transcendent intervention. For the stone, it doesn't make any difference whether a man pushes the stone, it's F equals m multiplied by a, or whether an angel pushes the stone. If the angel has the force to do so, then the stone has no other chance than to move, because it's a stone and it obeys the natural laws. So even this event is not something that breaks any natural laws, I would say. And in this case, if this is true, then it's also something extraordinary, because these things do not happen very frequently. If you do not believe this explanation, then of course that stones move is something that happens again and again. So then it would be, you would have to find another possibility, of course. So another case is here, coming back to this nice game here. Suppose we have a thought experiment. Suppose you want to win 10,000 euro and you play with a partner and say, if I win, I get $10,000. If you win, you get $10,000 euro, whatever. And now the situation is as this. You are on the red part here and it's your turn and you pray to get the dice to end on a 1. Then obviously you have won and get the 10,000 euro, but the other possibilities, of course, the other one gets a 2 and then he throws you out and then you have a problem. Now, you can pray and say, okay, Lord, help me that this happens. And you cannot, however, whatever happens, you cannot distinguish between divine action and probabilistic behavior. If you play with an atheist, the blue one is then an atheist, and you say, okay, well, so what? Yeah, it's just by chance. So there may be situations where you just cannot pinpoint divine action, and it's up to your interpretation or up to your belief to interpret what is happening. And there may be other situations where it's very difficult to deny that there is a divine action. So I've worked a little bit on distinguishing these cases, but I leave that out for the time being. Is there a contradiction between divine interaction and the laws of nature? The discovery of natural laws requires a reproducibility of deterministic or probabilistic processes. That is what we are used to have. And therefore, if, for example, you make an experiment and an angel or God or whatever intervenes, and this experiment ends up different than what you think. To be honest, what would you do? You just throw it out. You make another experiment. You would not, in your paper, you would not write, oh, there's an outlaw and this was an action of God, but I recorded it because it just happened. You would just throw it out. So divine action is by its nature not reproducible. And this is something also I would say to Andreas Beckermann and others, we have to have we cannot have the same requirements on reproducibility as in case of experiments we do otherwise. And the occurrence of miracles does not contradict a general regular behavior of nature. Now, I come to the conclusion. Due to deterministic chaos, quantum mechanics, and the vast net of causes and effects, the clockmaker's universe is dead. I hope this is quite clear. Natural laws on their own do not determine physical processes. Description of causal change cannot prove causal closure, but has to rely on causal closure. Conservation laws or causal change don't protect against divine action. And discrimination between divine action and probabilistic effects may not be possible in many cases. So with that, I would say the world is wide open for divine action. So with that, thanks for your attention.
Thank you very much, Professor Bergmann. I now invite Professor Christian Tapp from the University of Innsbruck for a response.
Well, ladies and gentlemen, as you may have noticed, the talk by Ralf Bergmann was very rich in material and thoughts and formulae and whatever. I had to pick out, say, 5 points to which I will make some comments only. The first point is on Bultmann. I think that Ralf Bergmann correctly pointed out that for Bultmann, the unacceptability of the New Testament worldview is not a conclusion, but the starting point of his exegetical endeavor. Since the Enlightenment, modern exegesis must take into account the great difference between the average outlook of a contemporary of the New Testament and modern human beings. We do not believe in demons, ghosts, and magical powers. This fact must be considered in the prerequisites of the hermeneutical method. Our understanding of the texts will be different from that of people who believe in that sort of things. Historical critical exegesis has led to many valuable insights into the diachronic development of Scripture. Is that better this way? It has opened ways to realize that biblical texts are a sacred document of faith that can be freed from accidental elements of ancient worldviews, and therefore can also be attractive for modern human beings. In this sense, it is in great continuity with the Church Fathers, who already held that the upshot of many biblical narratives is not the reporting of historical events, but testimony about faith in God's revelation in Jesus Christ. I admit that one may criticize biblical scholars for sometimes going too far when they assume the impossibility of certain types of events right from the outset, and without sufficient reasons to do so. In his account of Bultmann, Ralf Bergmann seems to have overlooked a little but decisive detail when he showed this inconsistency argument to us. With respect to Jesus of Nazareth, Bultmann does not say that God acts upon him, am Menschen Jesus, but that God acts within the life of a human being, in einem Menschenschicksal. This tiny difference is important because Bultmann does not conceive of Jesus as being situated vis-à-vis to a God who then operates upon him like upon an object. This would really be a contradiction to Bultmann's thesis that a human being is a unit closed to supernatural intervention. Bultmann's point is that Jesus' action is nothing but the action of God himself. This is at the center of what the theological term self-revelation means. To the next point, the topic of the first course. Bergmann says that the first beginning, the ultimate cause of the universe, cannot be described physically. I think this is perfectly right, but in need of little clarification with respect to the modal expression cannot. Here we have, I think, not an impossibility in principle, but as a matter of empirical fact. One can easily see this by a thought experiment. Just imagine that an omnipotent being has created the world exactly as it is, just say 5 minutes ago. Such a scenario is perfectly possible, and it would be a scenario in which the first physical status of the universe would be physically describable. That the beginning of the universe cannot be described by physics is due to the fact that our best cosmological theories describe the universe by a system of partial differential equations. Then we can calculate, numerically calculate, backwards along these equations, backwards in time. This comes down to extrapolating the processes we observe in the current era of the universe backwards as far as possible, namely until the solution collapses into a singularity. Singularities are sorts of dead ends for differential equations, because there the resolving function is not differentiable anymore. Having arrived at a singularity, we then invert the perspective and call this situation of emergence from a singularity a Big Bang. Hence, it would be more correct to say, when calculating backwards in time along our cosmological differential equations, we come to a point at which it is impossible in principle to calculate any further. All the rest is philosophical interpretation. Physics simply cannot give us any idea of what is behind the singularity. It may be a complete history of an earlier physical universe, or nothing, or God, or whatever. I'm not sure, but I think that Bergmann would agree with this view. The first cause of the physical universe might have been physically describable, but according to our best physical theories, as a matter of fact, it is a singularity and therefore cannot be described physically. Third remark concerning the notion of a law of nature. I think Bergmann is right that there is no single concept of law of nature everybody would agree upon. The more interesting question, however, is about the structure of laws of nature. Are the laws just deterministic universal statements? Are the laws statistical, talking only about probabilities of events instead of about events? And what are the antecedent conditions of laws of nature? Alvin Plantinga has proposed that laws of nature have antecedent conditions, such as if there is no influence from outside the system, then blah blah blah. This notion makes deterministic laws easily compatible with human and divine interventions. Such interventions then simply do not conflict with natural laws because they are influences from outside the system. One question for me here is whether divine and human interventions are really comparable to the extent Bergmann suggested. For if I lift a stone, my body will behave in complete accordance with physical law and the principle of energy conservation, for example. I will have used exactly the amount of energy the stone gains in form of potential energy if you just omit what I radiate as heat. But this is not the case if God intervenes, as he obviously has no body which could transform energy. So if he lifts the stone, ceteris paribus, then miraculously there would be additional energy in the system. Hence it is not completely clear to me why Bergmann thinks that the conservation of energy poses no problem for divine intervention. Fourth point, the notion of deterministic chaos. Bergmann has offered three arguments why the 19th or 18th century clockmaker's universe is dead. Because the universe is a dense set of causes that destroys uniqueness backwards in time, because there is deterministic chaos, and because of quantum mechanics. Let me now confess that I'm not a physicist. And let me then add that I am happy if a physicist tells me that the clockmaker's universe is over and done with. The only doubt I have is whether deterministic chaos really supports this claim. In deterministic chaos, as I have understood it, events are still governed by strict deterministic laws. It is just not possible to calculate the outcomes because of the complexity of the physical system under consideration. In philosophy, we usually distinguish between an ontological and an epistemic level. Ontologically, everything in deterministic chaos seems to be controlled, determined, and following fixed rules. Epistemically, however, with respect to knowing or to calculating, we suffer a lot of limits, like limited memory, limited brain capacities, limited computing capacities, limited knowledge of antecedent conditions, etc., etc. I think deterministic chaos is chaotic only on the epistemic level. It is just by far too complex to be computed by us, but in principle, with unlimited capacities, it would be computable. Hence, I do not see how deterministic chaos could rule out a Laplacian demon with unlimited cognitive power. And therefore, I cannot see that deterministic chaos would kill the clockmaker idea. In my view, deterministic chaos seems to me to lead to another conclusion, namely that the last truth about our universe may be opaque. Even if the universe were deterministic, we might not find out that it is, because we cannot calculate the outcome of systems with chaotic behavior, and therefore we cannot test any of our candidates for deterministic laws. I'm keen to learn whether Ralf Bergmann also thinks this may be the right conclusion from deterministic chaos. And last remark concerning the time arrow. I think that Ralf Bergmann is completely right that there is an asymmetry in the application of physical theories with respect to the direction of calculation. Even if we can calculate how a system proceeds from state A to a later state B, we cannot in general calculate backwards from B to A because there may have been quite different intermediate causal interactions that lead to the same results. The only question I would have is what the reason for this asymmetry is. Is it really that the physical description of one and the same system allows for different behaviors of that very system, even if there are no influences from outside? Or is it the case that the physical systems are just never free from influences from outside, so that we can never be sure about whether there was causal interaction from outside or not? To take up the terminology of epistemic versus ontological once again, is the reason for the asymmetry ontological? Is it part of reality? Or is it epistemic? Is it part of our description of the world? That would be my last question. Thank you.
Professor Bergmann, would you like to respond?
Yeah, thank you very much for this very useful reply. There's a couple of points. I don't know how much. Do I have another 40 minutes?
40 seconds.
Okay, 40 seconds, yeah. A bit more. So I think the consequence, to go to the first question, of Bultmann's theory is underestimated, because in the end effect, I believe that from what he says, I see the difference you say, but basically there is no way to implant ideas in Jesus or in other people. There is no way to implant revelations, because if you come from a naturalistic standpoint, then God cannot implant, if he then exists, if you are a naturalist, accept God exists. But if there is no interaction, then there is no chance of ideas or revelations or whatever to be implanted in a human and in any way to work on his life, because there is no interaction. So I think that should be taken serious. I think theology is digging its own grave with this pre-assumption. The second thing with the first cause, there is I'm sorry, I will not be able to answer everything, but in many cases we also agree, so I very much appreciate your comments. If there was a creation 5 minutes ago and everything was set as a complete universe with 13.6 million light years no, it's actually bigger, but let's say with these 10 billion light years or whatever it is, and we would measure the signal of a star, saying that was a supernova explosion 5,000 years ago or 5 million years ago or whatever, but the universe is only 5 minutes ago, then that poses for me the question, is this information fake? Because there was never a supernova 5 million years ago, but we get a signal from a supernova that has been exploded 5 million years ago. So I have a great problem with this idea of creation 5 minutes ago and just adjusting or 10,000 or 100,000 years ago, with just adjusting everything so as it looks like. Yeah? That would be a God that plays a game with us, because we would see things which never happened. Yeah, then the question with the ontology, I totally agree with Plantinga. I think the problem with the energy conservation is that we have no reason to say that God cannot bring energy into our space-time. I don't see anything that should forbid that. So if it would be necessary, I don't know why God should not be able to do it. And the question was ontological and epistemical. I think that's what I wanted to say. Whatever computer you buy and how much money you spend, you will not be able to definitely predict what deterministic chaos is doing, because it's doing something else every time, again and again. You can define strange attractors and things like that. So, which means you are in a certain area, the system moves only in a certain area of the phase space. But I'll be a bit more careful since yesterday, but I would say that maybe for further discussion, these situations are ontologic. It's not only epistemic. And it's no use to try to calculate better, because the system intrinsically produces this chaos. Yeah, the error of time, that's a good question. I always thought that it was entropy. Some people don't agree with that. So if the overall entropy of the universe increases, that's certainly has something to do with the error of time. Some people say it's in the development of quantum mechanics. I don't have a last answer, but the development of entropy certainly is one important outflow of for the time error. But I don't want to be too specific, because I don't really know whether that's correct in the end. So, okay.
Brilliant. Thank you so much.